Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Chris Smith. How's the world of science?
Well, it's been a very exciting week, actually. Obviously, we still have swine flu grumbling on around the world, and it's looking increasingly like this is going to be here to stay, and it's probably going to be the next pandemic. Whether or not it's a fatal pandemic, I think still remains to be seen. At the moment, we've got no reason to be too alarmed, but at the same time, we do need to keep an eye on it because who knows what's going to happen next. But I think one thing's for sure, and that is that there will be swine flu vaccine out in about 4 months' time. Scientists are strongly suspecting that this will follow the same pattern that previous pandemics have, and that in the same way 1918 and 1957's pandemics gave a blip in the summer, a big peak in the autumn, then a bigger peak the next year, and then a littler peak the year after. We think we're probably going to see the same sort of pattern with this. So at the moment, as the Northern Hemisphere goes into the summer, of course, flu viruses don't spread very well, and most of the world's population live in the Northern Hemisphere, so that's why we're probably seeing less activity than we would expect. And that's a blessing, because it's giving us this breathing space, now we know what the virus is, to make some vaccine and hopefully protect everybody.
Is 4 months going to be soon enough, though?
Well, that's a very good question, and the answer is we hope it is. I think people are making optimistic noises. It's a very laborious process making flu vaccine, and it has to be done in eggs. The way it normally is done is that scientists will take a look at what viruses are circulating on the other side of the world during their winter. So as Australia now goes into its winter time, there will be scientists, doctors, researchers, medics will be collecting samples of flu that are circulating in the Southern Hemisphere. They will be sent to the WHO, who will compare those structures, those viruses, against what we've got in the vaccine already. And if they're found to be grossly different than what's in the vaccine gets updated. If not, the vaccine remains the same. But the way it's made is that you take those flu viruses, you mix them with a strain of flu called PR8, which grows very well in chickens' eggs, and you get a hybrid virus that comes out, which looks like the one which you want to immunise people against, the one that's circulating, but also has the ability of PR8 to grow very well in an egg, and then you inject the virus into a chicken's egg with a chick inside it, so it's a fertilised egg. You leave it to incubate for a period of time, and then you wait till the virus has grown in that egg, then you suck out the contents of the egg, purify out the virus particles, chemically inactivate them, and then you've got vaccine. But here's the crunch. One egg makes enough vaccine for 3 people. So you need, just to treat the population of UK, 20 million chickens' eggs. And these are special laboratory-grade, high-purity, non-salmonella infected eggs. These are eggs that Edwina Currie would approve of. And that is not trivial to do. Now, if we want to treat the whole population of the world, of course, there are 6.7 billion people on Earth. That means you need in the order of about 2 to 3 billion chickens' eggs to make enough vaccine to treat the entire population of the world, because the thing about a pandemic is that everyone is susceptible. And that means that about probably 1 person in 3, if there's a really good-going pandemic around the world, will get infected. So we need to treat the entire population with a vaccine to stop that from happening, because that's very different than normal seasonal flu, which tends to prey on people who are elderly or very young, and therefore we target our vaccination at those people because they have the weakest immunity or no immunity, and therefore you don't need that much vaccine. When it's a pandemic, though, you do. So the race is on now to make sure we've got enough vaccine, and that's what people are beginning to do. It makes me wonder about our own immune systems now against these different viruses, because there seems to be almost a new virus that comes out every week, or they seem to be taking us longer to get over. Well, viruses are amazing, aren't they, if you think about it, because they're nothing more than an infectious bag of genes. They're tiny particles, about 1/10,000th of a millimetre across or so, some of them. Flu is about that ballpark. And they have become masters in hijacking cells. They take over a cell's function, turn it into a virus factory. The cell pumps out thousands, if not, in some cases, millions of new virus particles, sometimes killing the cell in the process. And the virus, as it does that process, changes itself, because many of these viruses don't have very good mechanisms for making sure that the genetic material, when they copy it, is a faithful copy. So they make mistakes. And so viruses that grow in a cell come out looking different than the virus that went in. And that's why you can catch things like the common cold, flu, and other viruses again and again and again, because they're very antigenically unstable. They change their appearance. And our immune system works because it's very good at recognising very specific structures. And because these viruses are constantly on the move, it's very hard to spot the same one twice. And so the immune system's constantly playing catch-up.
Oh, well, good stuff. Let's have our first question. This has come in by email, and it's from Paul of Ipswich. He said, it might border on the paranormal, this, but hopefully you'll be able to shed some light, Dr. Chris. He said he's now 50 years of age, but between the ages of 9 and 11, he started hearing strange voices in his head, and he doesn't think he's ever had a mental health or neurological issue at all. This would take the form of a single incoherent phrase whispered and echoed. It was pretty frightening at first, but then I almost got used to the phenomenon at the time. It could happen 2 or 3 times a day at any time, sitting at home in a quiet room or walking to school. 2 years after it began, it stopped as quickly as it started. As an adult, I suffer occasionally from tinnitus, and it was definitely a human voice. Could the tinnitus could have been a contributing factor? If not, any ideas? Psychological, physiological or paranormal? What do you reckon, Chris?
Well, I'm sorry to hear that you've had this, Paul, because it sounds a bit scary. It definitely sounds like an auditory hallucination. In other words, it's a complicated phenomenon which is experienced just by you, because we're presuming that Paul is saying that no one else could experience this, so it must have been coming from inside his own head, because obviously you've got to make sure that people aren't hearing something genuine. The fact that it was complex, it was a voice, and it was saying something, although it was saying something that may not necessarily have made sense, that still means it's probably an auditory hallucination. This is sort of similar, what he's saying, to what people who actually have auditory hallucinations when they have things like schizophrenia actually experience. The good news is that, of course, it went away. Why he had that transiently, though, I don't know. One possibility could be something like epilepsy. Not everyone who develops seizures goes on to have the kind of epilepsy that we associate with people falling to the ground and having a fit. Some people have what are called petit mal, or partial seizures. And in these cases, sometimes one bit of the brain becomes too active and it triggers off all kinds of funny sensations, but it doesn't necessarily make you lose consciousness. And it might have been that perhaps as he was developing, perhaps he'd had a knock on the head or some kind of head injury, which young boys are quite vulnerable to bashing their heads, because young boys, usually more than young girls, are more accident prone. And perhaps that had triggered a little bit of minor disturbance electrically in the brain, and that was what was making this happen, because we know from electrophysiological experiments, that means when scientists look at the brain, if you often in patients who are having brain surgery, doctors will be able to open up the skull and look at the brain surface and then stimulate bits of the brain or turn off bits of the brain with various techniques. You can elicit various phenomena for patients to experience by doing that. And what this tells us is that the brain is parcelled into different parts of the brain that do very specific jobs. And if you stimulate one bit of the brain that does a certain job, people experience a sort of hallucination driven and in the modality subserved by that bit of the brain. So in other words, if you stimulate the brain's motor area, the part of the motor area that you're stimulating of the body will move. So if you look at the brain surface, there's a virtual map of the body on it, and if you stimulate in one part of that brain, you can make someone's arm move, for example. If you stimulate the language part of the brain, you can make people say words, totally involuntarily. And it might be that perhaps there was some kind of electrical disturbance in the part of the brain that was concerned with audition, hearing, and it was feeding in these voices because it was having a sort of a miniature seizure or something like that. That's one possibility. It's very unusual for schizophrenia to come on at such a young age and also to go away again. Doesn't normally work like that, which is why I'm thinking outside the box. Maybe something else is going on. It may be something else. It may be that Paul was on some medication, because some medications can also make people experience hallucinations, especially painkillers. There are certain painkillers, especially those in the morphine, opiate class, which can make this happen. So there's a range of different possibilities. Without actually talking to Paul and finding out a little bit more about it, I couldn't say for sure. But in general terms, those would be my sort of top diagnoses, I think.
All right, let's move on to Peter in Wickford. He says, messages left on mobile phones. Some messages held in phones, some held in cyberspace. What is this cyberspace? Where is it? And is it secure? Chris?
OK. Well, what Peter's talking about is the internet, essentially, isn't it? Because this is the invention of Sir Tim Berners-Lee. He got knighted for inventing the internet. It was actually initially designed so that scientists could share data and communicate with each other, and it was to handle the vast amounts of data that were required to understand what experiments like those being carried out at CERN from particle accelerators were telling us. But pretty soon people realised that this kind of communication medium was very powerful. You could send messages all over the world in a fraction of a second. You could exchange information. You could exchange images. You could basically communicate and look up information very, very fast. And the way the internet works is that you have a massive distributed set of computers all over the world which are connected. And they're connected in a variety of ways. They can be connected physically on a network by a bit of copper cable. They can also be connected by fibre optics. So, in other words, you're transmitting data using tiny light pulses which travel at the speed of light down a glass fibre. That's fibre optic transmission. But the way it works is that you have all this data stored on different computers, and you have another set of computers that are called routers that know where those computers around the world are. And when you say, I want a piece of information off the internet, first of all, it goes to a local computer which knows which router it has to talk to, and that router then says the piece of information you want is stored on a computer on the other side of America or in Japan, and it then calls up that computer, gets it to send the data that you've asked for down the line via various routes to your computer. So when you say something is in cyberspace, what's actually happening is it's stored physically on a computer, probably on many computers, over this massive network of millions of computers all around the world. Now that's a little bit different with a mobile phone, because mobile phones, of course, are in your hand. They're a little computer in their own right, and they're communicating with a base station via microwave link. And actually they actually do use the internet as well, but basically when you have a text message coming through on your mobile phone, what's actually happening is that a message has been turned into a digital message, and it's then beamed to your phone as a microwave wave, which your phone knows how to decode. So it's slightly different. There's not ever anything sort of hanging in limbo. The data is always stored somewhere.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Agnes in Braintree would like to know, what is the cause of blood getting thinner as you get older?
I'm not sure that blood actually does get thinner as you get older. I think people tend to use that as a term to mean that you get a bit more fragile as you get older. What we do know about blood as you get older is that elderly people are more likely to have stickier, stodgier blood, which is more likely to clot inside arteries and cause problems like heart attacks and strokes. And the reason for that is given by, if you look at when it tends to happen in wintertime. And what we think goes on is that when people get older and the winter comes, then people are less good at keeping themselves warm. And in order to keep themselves warm, what they do is constrict down all their blood vessels, and to stop blood flowing near the surface of the skin, for example, which facilitates heat loss. So this is a way of conserving heat. And because you shunt blood into your core, this puts up your blood pressure. And when your blood pressure goes up, it makes the kidney filter more blood because it thinks your blood pressure is too high and it needs to get rid of some circulating volume. And when the kidney filters more blood, it also filters out very tiny proteins, including one called protein C. And protein C is an anticoagulant. And so what happens is that in wintertime, your blood, because it's a bit less full of protein C, is a bit more sticky. And this is why we think there are more heart attacks and strokes in wintertime than summertime. So I'm not sure you can argue the blood gets thinner as you get older. One thing that can happen with very advancing age is that your bone marrow can become less good at making the blood cells. And if you have fewer blood cells, then you can be anemic. So you can get anemia associated with old age. And this might be construed as a sort of form of thin blood. But thankfully, most people don't get too anemic if they eat a good diet as they get older.
Thank you. Let's go to Jenna in Kettering now. Dr. Chris, she would like to know about photos. How, when you take a picture, does the image go onto the camera film?
Well, these days, of course, we've largely replaced film cameras with digital cameras, but the principle is actually very, very similar. So let's look at a digital camera first, and then I can explain how a film camera works. What a camera effectively is a light capturing device. So you have a lens on the front of the camera, and the lens assembly is designed so that it can focus light, which is gathered from an area of the visual scene, and pinpointed that light onto a light-sensitive layer at the back of the camera. Now, in the case of a digital camera, that is a CCD, a charged coupled device. This is a semiconductor device which, when photons, the particles of light, hit that device, they mobilise electrons. In other words, they make a charge. They charge up patches of the surface of the CCD, the semiconductor, and the device, the camera, reads off from the CCD the amount of charge, because the amount of charge is proportional to the amount of light. And you can also have different layers that are sensitive to different wavelengths of light, which is how it discriminates colour, because different colours have different wavelengths. So, put simply, you have a lens which focuses light from an area in the visual world onto a point, which is your CCD chip. If you want to have a traditional old-fashioned camera, you just replace the CCD chip with some film. And photographic film, consists of a layer of gelatin, and underneath that is some celluloid into which is embedded the silver grains. And these are particles of silver nitrate associated with some halide salts, things like chlorine and bromine salts. And what happens is that when a photon of light hits those silver grains, then it reduces the silver from silver ions, Ag+, to silver, Ag. And so you get a black image, a black dot, where the silver is. And it's exactly the same reaction, effectively, that you see when silver is tarnishing, really. Basically, when you get silver that is being reduced back to silver from silver ions, then this is the same thing that's going on inside your camera. And the way in which you make colour film, because the reaction I've just described would give you black and white film, the way you make it colour is that you have different layers of the silver grains, and you associate each of these tiny grains, and they're just minuscule tiny grains, you associate them with a second chemical which preferentially absorbs light of different wavelengths and then feeds the energy from that light into the silver grain that it's associated with. And that's how you get different colours. And so you can have black and white film that has a single layer, or you can have colour film which has these sensitising chemicals associated with the silver. So that's how a camera works.
Excellent. More questions coming up for Dr. Chris now. This next one from Keith. He recently heard of a rocket with a telescope being sent into space to do exploration. I wanted to know, says Keith, what we will gain out of these voyages, and couldn't this money be spent on such missions be better spent sorting out problems on our own planet? What's your view, Chris?
I suspect that Keith is talking about two probes that were launched this week, which was Herschel and Planck. And these are named after, obviously, very famous scientists. But these two probes will be able to look into space deeper and in a different wavelength than we've actually been able to see before. What they'll basically be able to do is interrogate space for some of the answers to things like the Big Bang. They'll be looking at things like the polarisation of light from the Big Bang, because at the moment we understand very little about how the Big Bang actually happened. In other words, the huge catastrophic explosion that spawned our universe. We just don't really know what happened immediately before the Big Bang, during the Big Bang, and after the Big Bang. And it might be that written into some of the radiation, the cosmic background microwave radiation that's still knocking around, which is a vestige of that early light given out during the Big Bang, there may be written into that a sort of signature of those early events when the universe was born. And so by studying these kind of things, scientists are able to understand a lot more about the world around us and how we came to be. So they're quite important questions, because we want to know whether we're alone in the universe, or whether there are multiple universes. Are there other universes, a bit like this universe, hovering around us that we can't see? And so we obviously want to understand these things, because this is fundamental to the human quest to understand where we came from and where we're going. In terms of whether this is valuable, I would argue that it almost certainly is, because there are many examples of things that have been developed for space which can have applications on Earth too. And one of these was presented to me this week, in fact. I was talking to one of the microbiology doctors at Addenbrooke's this week, and he said a person came to see him from London recently, and this person had with him diagrams of a probe that was built for Mars to go looking for life. And the way it goes looking for life, this robot, is that it shines a laser on a surface and it looks at the scattering of light that comes back, and it can analyse the light that's being bounced back to see what chemicals must be in the surface substances it's looking at. And by interrogating the surface like that, you can begin to say, well, are there any chemical hallmarks of life here? He's saying, well, actually, the same technology could be used to see if we've cleaned our hospital wards properly, because by doing the same device with a handheld thing that doctors could wave around, or nurses, cleaners, the person who comes around to make sure a patient's bed is clean, these things could be scanned around a surface to see if there are stray bugs or if there's contamination. Now, no one would have gone down the line of developing that kind of technology if it wasn't for the fact they were trying to solve a problem in space. So sometimes having even an unassailable problem to tackle develops spin-offs which have huge benefits. And another really good example here on Earth is something called the Riemann hypothesis. The idea is that there are prime numbers that go on ad infinitum, we think. Prime numbers are important because we use them for internet security. We use them to encode things so people can't break the code, and this means that things like your bank transactions online are secure. But scientists would like to know if there's a way of predicting prime numbers and knowing where they are and working out what the next one is. That's called the Riemann hypothesis. There's a prize that was laid down by Riemann. I think it was $1 million for the person who could come up with a solution to this puzzle, whether or not there was a formula that would predict prime numbers. No one's ever solved it. It's still standing there, waiting to be claimed. But in the course of trying to solve the Riemann problem, scientists, mathematicians have gone down routes they would never have otherwise explored, and this has turned over new fields of mathematics. It's led to the development of whole new approaches to maths. And inevitably there have been spin-offs for the maths we can do. Just by trying to do some maths we can't. I think the same applies in the space race and applies to lots of things here on Earth. So I'm very much in favour of trying to solve hard problems that inevitably dealing with space involves, because there are always spin-offs that are for the good.
A little bit like clearing out the cupboard and then discovering something you never knew you had. All right.
Absolutely.
OK, let's go to Mike in Colchester now. He says when he tears a newspaper downwards, he gets a fairly clean tear. However, when he does this from right to left, it's always a mess. Why is this? That's a good question, isn't it?
Very good question. It comes down to the structure of paper. Now, what he's asking is, why is it that with things like with newspapers, if you try and tear that token out, you can tear half the token out in one direction really neatly, but when you try and go down the page, you just get this horrible jagged mess, and it's obvious to everyone what you're doing, because you're trying to surreptitiously take the token out from the tea room newspaper, and you make a horrible mess, and everyone then stares at you. The reason is all down to the structure of the paper. If you take a newspaper and look at it with a magnifying glass, and then make the paper a little bit wet, you can tease apart the fabric of the paper, and it's best to use cheap and nasty paper for this. Tabloid newspapers, no disrespect to them, but they use fairly cheap and nasty paper, and this is brilliant for seeing this effect. And if you tease apart the paper with a drop of water on it, you'll see fibres. And that's because the way you make paper is you make wood pulp. So you take wood chips, you put lots of water on them and grind them up, mash it up, and you get down to the individual, what are called fibrils, little particles of wood. Wood is a chemical called cellulose. This is lots of glucose molecules jammed together or glued together, and they form rigid little sticks. They're almost like miniature cocktail sticks. And so because you've got these fibres, when they make the paper, these fibres lay down on the paper and they form a sort of crosshatch pattern, and they mishmash together, all overlapping each other. But there tends to be an orientation in which they line up better. Because if you imagine something which is lots of long, thin matchsticks, then they'll line up in one direction because they can get closer together in one direction than another direction. And this means that there's a point of weakness which is tearing parallel to your matchsticks, but it's much harder to tear across the matchsticks. And because of the way the paper is made and then rolled between rollers, you tend to get these things lining up preferentially in one direction. And that means the paper is weaker in one direction than another direction, and that's why it tears better. And the way you can solve the problem is if you artificially weaken the paper in those orientations, in other words, by putting a fold in and then bending the paper over hard and pressing down hard across the fold and then undoing it again and then tearing, because what that does is it puts weakness and breaks some of those individual little cocktail stick-shaped fibrils of cellulose and makes them easier to tear.
Thank you very much, Dr. Chris. Dr. Chris, Valerie in Littleport, says that she just got back from holiday, and while she was away, she saw 2 rainbow rings around the sun. She's seen something like this before, but she wonders what causes it.
Yes, the reason for this, and it's very pretty when you see it, and it can also occur around the moon. You sometimes see these halos around the moon, and especially on very cold, clear nights. And it's down to ice crystals high up in the atmosphere. You have very high up in the atmosphere tiny ice crystals that are a hexagonal shape, and when they get hit by the sun's light, what they do is to bend the light by about 22 degrees. And that's important because what that means is that when the light gets to your eye thinks that, having interpreted the angle it's coming to you from, the light must have arrived from actually outside, around the sun, not from the sun itself, because the light's been bent inwards a bit like a lens. So it's an optical illusion, and your eye projects the origin of that light in a ring, a halo, around the sun. So you get these rings around the sun, and they're at about 22 degrees. If you were to look really, really carefully, you might see another one. You can see this around the moon better because, of course, the contrast with the dark sky makes it easier, but you'll see another one at 44 degrees around the moon.
Now, Anne says, Dr. Chris, can you take aspirin and anti-inflammatories at the same time?
Well, aspirin is a kind of anti-inflammatory. Aspirin works by turning off an enzyme called cyclooxygenase, and cyclooxygenase is one of the enzymes, one of the pathways, which is involved in making inflammatory chemicals in cells called prostaglandins, and prostaglandins wind up nerve cells, they make things become inflamed, and they trigger pain. Aspirin inhibits that process. There are other anti-inflammatories which work exactly the same way as aspirin, and therefore taking those at the same time as aspirin means you're more likely to get lots of negative effects, things like bleeding and ulceration and perhaps damage to your kidneys and other organs, maybe even your ears, and fewer positive side effects. So if they work in the same way as aspirin, it's a bad idea to mix them. So ibuprofen and aspirin both work in exactly the same way, and therefore taking them at the same time as each other is dangerous. But there are other kinds of anti-inflammatory which you can safely mix with aspirin because they work in a slightly different way, and paracetamol is a very good example of this. If you mix paracetamol, acetaminophen, with aspirin, the two work synergistically, they work together, but they work through different mechanisms, and so the effect is additive. They're not competitive. So in other words, it's quite safe if you've got a very, very bad headache to take 2 paracetamol and 2 aspirin 2 hours later, and you can sort of overlap the doses of those two things as long as you don't exceed the dose for each of the 2 different painkillers, and this can provide much better relief than just taking one of those 2 agents alone. I actually did that when I had glandular fever when I was 25. I've never felt so ill in my life, and the only way I made myself feel vaguely okay was by taking paracetamol every 4 hours and then aspirins in the 2 hours after I'd taken the paracetamol every 4 hours. And so by mixing the two together, I achieved some degree of sort of comfort. But so you have to be very careful that you know how these things work, not to mix ones that work the same way. But aspirin and paracetamol are okay, as long as you're okay taking aspirin.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.